In this video, we're looking at something called the king rule for definite integrals. And I've written down what it is right here so you can see it. It says that the integral from a to b of f of x with respect to x is actually identical to the integral from a to b of f of a plus b minus x dx. So as an example of that, what I'm saying is take any function you want. Let's say the integral from, let's put numbers in, right? Let's go the integral from 1 to 2 of sine x, something like that, just as an example. What I'm saying is this is actually the same thing as the integral from 1 to 2 of sine of the two limits added together, so 1 plus 2, which is 3, minus x. Okay, so in this situation, that's not very helpful, right? Why would we want to do that? We wouldn't want to. But there's plenty of examples, and we're going to look at some in today's video, where actually being able to rewrite the integral like this allows you to solve it. And also, stay tuned until near the end of this video because I'm going to show you another formula that's related to this that's even more helpful, you could argue. So let's actually have a look at, first of all, deriving this identity, this formula, this King's rule. So by the way, the king rule is not named after anyone. So it's not someone's name. There's no one called king as far as I'm aware. It's just a name that's caught on, basically. So don't try and track down who did it. So let's actually begin by trying to prove it. So we'll start with the integral from a to b of f of x. And what we're going to do is we're going to do a substitution. So we're going to let u equal a plus b minus x. Okay, and you're going to see why this is useful in a second. It's pretty much it's mostly about the benefit of the limits here. So this integral is equal to, let's see. So the lower limit is when x is a. So when x is a, u is a plus b minus a. That's b. And the upper limit is when x is b. So u is a plus b minus b, which is a. This is kind of why that substitution works, because it does this clever thing of swapping the limits around, and you'll see that we can put them back later. And then we've got f of, and then x is just by rearranging this ever so slightly, it's going to be a plus b minus u. And we can see here that du dx is the number -1, which means du is minus dx. So I can replace the dx with a du, but I've got to put a minus sign somewhere. So I'll put the minus sign there for now. Now, guys, there's also a rule of integration that says that you can swap your limits of integration around if you multiply the integral itself by -1. And because there's already a minus there, what I can do is I can rewrite this as the integral from a to b again, and I can get rid of the minus as well. So all in one step, I'm getting rid of the minus and I'm swapping the limits around. And then I've got f of a plus b minus u du. Now, guys, u is a dummy variable. So that means it's not going to appear in the answer. It's just a variable that we use to actually get the function integrated. So you can replace u with whatever letter of the alphabet that you want. So I'm just going to put it back in terms of x just so it looks a bit nicer. So I've got the integral from a to b of f of a plus b minus x dx. And there we go. We've successfully proven the result up here. So the integral from a to b of f of x with respect to x is actually the same thing as, it's identical to the integral from a to b of f of a plus b minus x. That's how it's done. So it's just a simple substitution, but it's kind of a remarkable result, I think. It's pretty cool. Anyway, let me make a case to you why you'd actually want to use this, because at the moment, we've not looked at an integral that would benefit from making this change. So let's look at that right now. Okay, so here's an integral. The integral from 0 to pi over 4 of the natural log of 1 plus tan x. And I've rewritten the king rule in blue there for us. So what we're going to do is just use it. So I'm going to label this integral I, just so that we can refer back to it. We're looking for what I is. And I'm going to say that I can also write I as the following. It's the integral from 0 to pi over 4 of the natural log of 1 plus tan. And again, I'm just using the king rule. So what I can do is I can replace all of the x's in the function with the two limits added together minus x. Okay, so the two limits added together here are 0 plus pi over 4, so just pi over 4, minus x. And again, you might not think that this looks any better, But what we're going to end up with is something really, really cool here. But what I've said is that both of these integrals have the exact same value. But the benefit of doing this is this can actually be simplified quite nicely because we have tan of something minus something, which allows us to use one of those compound angle formulas. So let's continue this simplification. We've got the integral from 0 to pi over 4 of the natural log of 1 plus. And then guys, down here, I'm going to do it in a different color for us. I'm going to write down the compound angle formulae for tan of a minus b, okay? So tan of a minus b is actually identical to tan A minus tan B over 1 plus tan A times tan B, like that. So that's called the compound angle formula for tan of A minus B. And you can see that that's exactly what we are dealing with here. So we can certainly use it. So we've got tan of pi over 4 minus tan of x divided by 1 plus tan pi over 4 times tan x, just like that, close bracket, dx. Now, it looks like we're making it way, way, way harder than it actually should be, but you guys will see that it all just collapses down and simplifies very, very, very nicely. So we've got the natural log of 1 plus, and then, guys, tan of pi over 4 is the number 1. So we've got 1 minus tan x on the numerator, and on the denominator, we've got 1 plus tan x, because again, tan of pi over 4 is just the number 1. Okay, and then one more step here. Let's rewrite this as the natural log of just one big fraction. So this is the integral from 0 to pi over 4 of the natural log. And what I'm going to do is I'm going to rewrite the number 1 as 1 plus tan x divided by 1 plus tan x. And then let's rewrite the other fraction just for, exactly what it is. It's 1 minus tan x over 1 plus tan x. Okay, and you guys can see that this really does simplify quite nicely. So we've got the integral from 0 to pi over 4 of the natural log of, and then if we combine these because they have the same denominator, we've got 1 plus tan x plus 1 minus tan x, all divided by 1 plus tan x. So that's 1 plus 1 is 2, and the tan x's cancel out on the numerator. So it's just 2 over 1 plus tan x. And guys, you're going to see how this all comes into place right now. So using a rule of logarithms, I can rewrite this as the natural log of 2 minus the natural log of 1 plus tan x. Remember, that's just a rule of logarithms. And this is the best part about it, guys. If we go back up to the original integral, what we're trying to actually find the value of is the integral from 0 to pi over 4 of ln 1 plus tan x. We've got that down here as well. So we're going to end up getting one of those I equals something minus I situations. You'll see exactly what's about to happen. So if we split this into two integrals, we've got the integral from 0 to pi over 4 of just the natural log of 2 dx minus the integral from 0 to pi over 4 of the natural log of 1 plus tan x dx. And guys, remember, this is I. This is what we've done, right? So we've started with this version of I, and then we've used the king rule to come up with a different version of I, but they have the same value because of the king rule. And we've rearranged this new version, and it's basically turned out that the original version is inside the new version. So what we have is that the original integral is equal to the integral from 0 to pi over 4 of ln 2 with respect to x minus, this is I again. So this integral here is I again. So all we have is that I is equal to this integral, the integral from 0 to pi over 4 of the natural log of 2 dx minus I. And of course, this is nice because the integral of the natural log of 2 is really, really, really easy. So adding I to both sides, we have 2I, and that's equal to the integral from 0 to pi over 4 of the natural log of 2. What is that? Well, if we integrate the natural log of 2, we will get the natural log of 2 times x, because remember, the natural log of 2 is just a constant. It doesn't integrate any differently to the number 1 or the number 2. The natural log of 2 is just a constant. And so we have 2I is equal to the natural log of 2 times pi over 4 minus the natural log of 2 times 0. So obviously we have that 2i is equal to, this is just the natural log of 2 times pi over 4 minus absolutely nothing. So I'm going to write that as pi over 4 ln 2. So that means that I can finally say that I is equal to pi over 8 times the natural log of 2. So what we've found is that this integral, the one that we've started with, this ends up having the value of pi over 8 times ln 2, which I think is a really satisfying answer. It's got a bit of ln, got a bit of pi, really cool stuff. So the way that we've done that, again, is by using this king rule. We start off with something that we can't really do much with. We end up doing the king rule. We get another expression and it all just kind of falls into place. So this is a really powerful idea. Now, as promised, I'm going to show you an even crazier thing that you can do with the king rule involving a more general class of functions. So there is a class of functions that I'm going to tell you about in a second that you can basically instantaneously find the indefinite integral of, as long as you know this more advanced version of the king rule. Let me show you exactly what I mean. So before we get started, I've just rewritten the king's rule again here just so we can see it. And all we're going to do here is we're just going to use the king rule. But instead of f of x, we've got this whole thing here. But it's the same idea, right? So if you want, you could rename this entire fraction. You could just call it like g of x or something. And then you could use the king rule on that if it helps you. But let me show you what I'm talking about, right? So we've called it I. I is going to be equal to the following. The integral from a to b of, and again, using the king rule, every time you see an x, replace it with a plus b minus x, okay? So we've got f of a plus b minus, and then x is getting replaced with a plus b minus x. So a plus b minus x, like that, okay? And then same thing over here. I know this is a bit more complicated, but we've got f of a plus b minus a plus b minus x plus f of, and then this one's nice and easy, a plus b minus x. So all we've done here is we've just used the king rule on a more complicated situation. But what happens is it ends up simplifying so nicely. So we've got the integral from a to b of, right, what is this? We've got a plus b minus a minus another b and then minus x. So that's just f of x, just plainly. This one down here is the exact same. It's just f of x. And this over here is f of a plus b minus x. Okay, cool. So if you compare what we've got down here to what the original is, then you can actually see that this is the clever bit. If you add them together, you'll get the integral of the number 1, right? This is the clever bit. So this is one version of I. This is another version of I. Remember, we don't yet know that this is true, so ignore that. We don't know that that's true yet. So let's say that's a bit of a mystery. All I'm saying is to take this version and this version. They are the same thing. Because of the king rule, we know they're the same. And all we're going to do is add them together. So 2i is going to be equal to the integral from a to b of just them added. So f of a plus b minus x divided by f of a plus b minus x plus f of x. And then we're adding the other version, so f of x over f of x plus f of a plus b minus x, like that. Okay, and guys, you can see that if I write this as one big fraction, I do indeed just get the number 1, right? Because it's f of, they have the same denominator, f of a plus b minus x plus f of x. That's the numerator. The denominator is f of a plus b minus x plus f of x as well. So this is the same thing divided by itself. So this is just the number 1 here with respect to x. Hopefully that makes sense. And that means that 2i is equal to the integral from a to b of the number 1, which is the number 1 integrates to x, and then we evaluate it between a and b. So we've got that 2i is equal to b minus a, which means that I does indeed equal b minus a divided by 2. And that's really cool. So now, just to show you that, of course, we can go over here. This is basically what we've just proved. So this is, if you want to, like, if anyone's making notes or something, you want to write anything down, or if you just want to make a mental note of it, we've just proved that this here is true. And this is just a consequence of the king rule. And so what we'll do now is look at an example, and I'll show you there's a really hard integral, and actually just boom, like that, it's nice and easy. Okay, so let's take a look at this integral. It's the integral from 0 to pi over 2 of cos to the power of 100 divided by cos to the power of 100 plus sine to the power of 100. And I've rewritten down the new version of the king rule that we've just derived. Now, you guys can see it's not immediately obvious, but actually the integral is indeed in the right form, because cos and sine have this nice relationship between themselves. So remember, cos, I can rewrite that as sine, still to the power of 100, of pi over 2 minus x. Okay, this is because, by the way, sine of pi over 2 minus x is the same thing as cos. Also, cos of pi over 2 minus x is the same thing as sine. So you might not know that, but that is true. And that can also be proven using the same, those compound angle formulas. But what I'm saying basically is you can rewrite the function like this. So they are the same just by literally rewriting it in a slightly different way. And hopefully now it's really clear to see that actually, yeah, this does work, because on the numerator, you've got this function f of two numbers added together. They're the same as the limits because it's 0 plus pi over 2. So that pi over 2 is a plus b, and then minus x. And so you do have that. And all I'm saying is in literally one go, we can go, okay, this is the upper limit, which is pi over 2, minus the lower limit, which is 0, divided by 2. And that's going to give us pi over 4. Look at how easy that was. Even it's literally, I go, blah, blah, blah. Don't know if you guys heard that, but it's literally thundering right now because of how colossally epic that is. So we have done a bit of King's Rule, a bit of the King Rule. Thank you guys for watching. I hope you enjoyed it. Let me know if you want to see anything else on the King Rule of integration. There's also a Queen Rule, and there's also a Jack's Rule or Jack Principle or something like that. So there's a bunch of cards, decks of cards going on. Let me know if you want to know what the Queen Rule is. Let me know if you want to see more videos on integration. And as always, guys, I'll see you in the next one.